In this video, we're going to talk about molecular shapes of molecules and applying dipole moments to these different molecular shapes so that we can tell how molecules interact with each other. That's our ultimate goal here, is to describe the electron density inside of molecules so that we can describe how they interact with other molecules like themselves. So first off, we have to understand molecular shapes of molecules because these are 3D structures. We always draw them on paper, but of course these are 3D things and they exist in a 3D space. So we're going to learn 4 main electron domain geometries in this class. I know there are more, so if you've had chemistry before, you might know some other ones, but we're only going to study these 3 electron domain geometries and their corresponding molecular geometries. So this is what we call here an electron domain geometry. Now I know it says electron pair geometry, but it's the same thing, electron domain geometry. And this describes the location where electrons reside around a central atom inside of a molecule. So we have linear, which is flat like this. Here's our linear. We have trigonal planar, which is also flat. So it's just like a triangle, a flat triangle, kind of like this with atoms at each corner. And then we have our tetrahedral, which is not flat. These two are flat. This one is 3D, and it has 4 electron areas around it. And this is kind of like, I like to think of it as like 2 and 2, and then they kind of go together like this. So, and that's kind of our 3D shape, if that helps you remember it. That's a tetrahedral molecule where it has 4 areas of atoms or electrons around the central atom inside of a molecule. So an example of this might be like CO2 here for our linear. For our trigonal planar, we have boron tetrafluoride right here. Nitrogen dioxide, you can see here as well. Tetrahedral, we have 4 atoms off the central atom. Something that you'll notice is we have molecular geometry. So let's talk about molecular geometry. So for each electron domain geometry, we have corresponding molecular geometries. Now the difference between these 2 names is that one accounts for lone pairs and others do not. So lone pairs are unpaired electrons, lone pairs are non-bonding electrons. So lone pairs, these are non-bonding electrons. So we often see lone pairs around our exterior atoms like this here, but not too often do we see them around our central atom like this here with our nitrogen dioxide. When this happens, when you see a lone pair around your central atom inside of a molecule, we name it differently when we use molecular geometry. So you see here that trigonal planar, when you have 3 atoms around the center, is also called trigonal planar molecular geometry. But as soon as we change one of those atoms into a lone pair right here, it gets a different name. And this is called a bent structure instead of trigonal planar. So it has 3 areas in which electrons or atoms reside around the central atom, but now it's got a different name. Same with tetrahedral. So tetrahedral, if all of the electron density areas around the center of the molecule comprise atoms, then it's also called tetrahedral in molecular geometry. But if you have any of these atoms as lone pairs around the center of the molecule, like in our nitrogen and our ammonia here, so our nitrogen, I guess trioxide is one way you could say it, but it's called ammonia as well. That's our common name. We call it something else. It's trigonal pyramidal. If you have 2 lone pairs like water, it's called a bent structure. So trigonal pyramid, I remember this because if you look at the 3D, it's got a base of a triangle. So here's this is A right here, sorry, and here's B. I like to visualize it like this. And these all kind of, here's the lone pair up here, and these all connect to the lone pair around the center A atom. So if you look at that, that's like a pyramid, and the base is a triangle. So trigonal pyramidal always makes me think of that structure. Okay, so these are our main molecular shapes, and we're going to apply our dipole moments to these in order to see kind of how the whole molecule is electronically. We talked about all of that, so don't worry. All right, so the main difference between the two geometries that we described are the lone pairs. Okay, so these are non-bonding electrons. That is the definition that we described. Same thing, they're pairs of valence electrons that are not shared with another atom. That's the same thing as non-bonding electrons. Okay, so your electron domain geometry that was on the left, the linear, the trigonal planar, and the tetrahedral includes lone pairs in the molecule shape, and your molecular geometry does not. It names them something different if they have lone pairs. Okay, so see if you can name these now. This is going to be your opportunity to do this. So I would encourage you to download this Molecular Constructor app. It's going to let you actually model these atoms that are here. So I'm going to walk you through how to do that. This is a free app, so you can download this on your iPad. Let me show you where it is on mine. Molecular Constructor. You can go down here where the File button is, button. You can go to Add, and you can select the element that you want to add. You can click on it, click once on your screen. You can add another one. So here for nitrogen, we're doing ammonia with our nitrogen trihydride. Sorry, 1, 2, 3. If you want to connect these by a bond, you simply click on one of them and drag it to the other. I think you double click. Hold on. Yes, you double click and click the other one. Okay, close. Okay, so if you click outside of the atom, like on the screen around it, it will unselect it. So we're going to do that again. Select the center, select the one you want to bond, click on the blue around the area, and it will unselect the main one again. And there and there. I think if you don't unselect it, it will like try to connect all of the atoms strangely. So make sure you click the blue space around it. Okay, now what we're going to do is this has an optimizer tool in it that's going to just automatically put the shape on it for you. So do you see the shaping button here at the bottom? It says shaping, and right now it's off. So we're going to turn that on. Cool. All right. Okay, now turn it back off so it'll stop moving around. And now you can take this molecule and you can drag it around, and you can see the structure of it. So beforehand, before shaping, it can be any shape, right? It might be something really weird that's not quite right, but as soon as you push the shaping button, it's going to fix that for you. So this is kind of a way for you to figure out the shape before we learn how to do this on our own. So we'll learn this eventually in another topic. Okay, so give this a shot. Go ahead and download Molecular Constructor and see if you can find the electron pair geometry or electron domain geometry, and the molecular geometry for each of these molecules here. So let's look at the answer to this problem. NH3 we actually did in the example problem. It is a tetrahedral in its electron domain geometry, hedral, so EDG, because it has 4 areas around the atom here. It's got hydrogen. And you can see that in the shape because the hydrogens are kind of pushed down. If it was trigonal planar, they'd be flat like this. So that's how we know it is a trigonal pyramidal for our molecular geometry. Okay, so our molecular geometry. For HCF, you should have seen something like this with the fluorine, and the hydrogen in the center. And this one is tetrahedral, and this is also tetrahedral because there are no lone pairs around the center. For our carbon, we're going to have carbon, O, O. This one's going to be linear and linear. If you had any trouble with this, especially with the app, I would chalk it up to the app. You will have more problems on your homework that are going to be more clear about this, and you'll be provided structures for this topic if you're asked about molecular shapes. Like you'll be given those and you'll have to figure out the names of them. All right, let's take a look at what a net dipole moment is. A net dipole moment is kind of like a combination of all of our dipole moments. So remember that our dipole moment is between two atoms with different electronegativity. So if they have a difference of electronegativity, then we have a dipole moment. They can have different magnitudes. Some of them can be big dipole moments with a big difference in electronegativity, or they can be really small. And when we combine these dipole moments, sometimes the direction in which atoms pool can cancel each other out. So for an example here, we look at carbon dioxide, right? So carbon dioxide has a dipole. We see these bond dipoles here in between our carbon and oxygen. They pull differently. The oxygen's actually pulling more. It's pulling electrons towards it, so there's more electron density there. But they're pulling equally in opposite directions. And so what that means is that overall, one side of the molecule is the same as the other. And therefore, it has no net dipole moment because the direction of this charge cancels out. So one is pulling this way and the other one's pulling this way. And just like a tug of war, they're both pulling equal but opposite directions. So at the end of the day, no one moves anywhere. However, if we have a molecule that's bent like this, even though it's almost similar in structure to our carbon dioxide, we've got a central atom, two atoms off the center that are exactly the same. The difference here is the shape and the direction of the dipoles. So if you'll notice, the dipoles are kind of pointing up this way towards the oxygen. They don't cancel out. If they were flat like this, they would cancel out because they're equal in opposite directions. But because they're this way, we're going to see that there's a partial negative charge kind of up here and kind of a partial positive at the bottom. This one, there's not really a dipole. There's no dipole moments. So let me make this distinction. There are bond dipoles. So between the carbon and the oxygen, there's a bond dipole, but overall, there's no net dipole moment. Okay, so net dipole moment is the sum of all dipoles and their directions. So let's look a little further at this. How do multiple dipoles interact within a molecule? So how do multiple dipoles affect partial charge of a molecule? We had kind of see that in our carbon dioxide here, and we had seen that in our water here as well. So charges, again, can cancel each other out. If they are equal in magnitude and opposite in direction, then they can cancel each other out. So they might be pointing both this way or both pointing both this way, and they can cancel their direction. So what I like to think of it as, here's a nice example up here as well with the carbons with the bromines and the hydrogens off of them. We can see that the bromines are pulling this way in equal but opposite directions, so they kind of cancel each other out here. But if you'll notice, we've got a hydrogen on top and we've got a bromine on the bottom. If you look at the Pauling scale, bromine is going to pull differently than hydrogen. I think it pulls more than hydrogen. So it's going to be pulling electrons towards it more than hydrogen does, meaning that this side's going to be more negative and this side's going to be more positive because there's a higher electron density down there. So we represent that with these arrows. So we represent arrows to show the direction in which the electrons are being pulled. So if we put a positive on this end, that means it's going to be partial positive. And this end of the arrow is partial negative. You'll also notice that the arrows in this molecule are different sizes. They're different magnitudes, different lengths, and that matters. So this hydrogen one is smaller than the bromine one, indicating that bromine is pulling more. You'll see that these, let's see. So we have this difference in magnitude of the pulling of electrons. Now I want to explain briefly this hydrogen thing, so it might help you a little bit, or the water thing. It always helps me to kind of think about bond dipoles when they're at an angle like this, like a 45-degree angle or something, as being comprised of two different components. So think about when you have a slope here on a line. We've got our rise over our run, right? So anytime we have something that's kind of like at a angle like this, we have an up vector and an over vector. And so we can kind of split our forces into two vectors. So in water in particular, you can see that this bond dipole that is at an angle has two components. It's got its horizontal component and its vertical component. And so the horizontal components, these cancel each other out, meaning that the main pull here is upwards towards the oxygen because the hydrogens are equal, opposite directions, so they cancel each other out. So we're seeing this upward pull. So in general with water, even though your dipoles, your bond dipoles are kind of diagonally like this, we see this side is partial negative and this side is partial positive because this pulling here with the hydrogens, they kind of cancel each other out. Okay. This will make more sense when you do more examples. So let's look at a couple of rules that are going to help you understand how to draw these arrows. So when you draw dipole moment arrows, the less electronegative atoms is where you start your arrow. That's where the positive side goes. So this is a lower En. And this is a higher electronegativity. That's how we always draw these. And sometimes you may need a Pauling scale to figure this out. So it's okay if you need to use a Pauling scale to figure out the direction of your arrows. If you have a bigger dipole moment, a bigger difference in electronegativity, difference in En, that means that your arrow is bigger. It's showing that that magnitude is more. So carbon and oxygen have a smaller difference here, so their arrow is smaller. Oxygen and hydrogen have a much bigger difference, so the dipole moment arrow there is much bigger. Okay. Arrow just need to show the... Okay, so the arrows just need to show the difference. They don't need to be an accurate size. So it's just kind of showing one's bigger than the other, but again, there's no really a good way for us to figure out what size the arrow should be. Okay, so if you have equal force in opposite directions, those forces do cancel each other out. Okay, so this is where we have a new definition. If all of your forces cancel out, you have no net dipole. And we call this term nonpolar, where there's no net dipole. So go ahead and write this down. This is very important. If all of your forces in your molecule do not cancel, there is a net dipole, then we call this molecule polar. So there is a net dipole. So this would be a nonpolar molecule, and this would be a polar molecule. So let's look at some examples of this. This is affected by our molecular shape. If we have equal but opposite directions in our forces, then we have no net dipole. So specifically, some trends in these arrows to look for are when you have two arrows, again, they're pointed towards each other or opposite each other, and they're linear. Another, when you won't see this, is maybe you have two arrows pointing in the same direction, and there's nothing to cancel them out. Or maybe you just have one arrow in one direction, one arrow in another direction. There's nothing to cancel it out on the other side. Some notable exceptions to this equal but opposite force are when you have a trigonal planar molecule that has the same atoms around it. So if you have the same atoms, they're pulling the same amounts. This also has no net dipole. Because if you split all of these forces into horizontal and vertical components, like we saw our diagonal lines doing, or diagonal vectors doing, you'll find that, that there's a down component and an over component and a down component and an over component. So the over components cancel each other out, and these down components here cancel this one as they are additive. So that would mean there's no net dipole here. Same with this one. We can draw that same principle. There's the down forces and the over forces, and they cancel out the other ones. This would not hold true if you had different atoms. So if you had, say, like a boron with a hydrogen and two fluorines, now this guy's polar, because hydrogen pulls a different amount than fluorines. So those forces won't exactly cancel each other out. You can say the same with the carbons. If you had carbon, say like a hydrogen and 3 fluorines, it's not nonpolar anymore. It is polar. It's going to have a dipole because this pulls differently than all of these, and they won't cancel each other out. So do be aware of these. Make sure you can recognize them because that might be something that comes up that might be a little bit hard to recognize. Okay, there are a lot more options in general for molecular shapes that are polar and nonpolar. You're going to do a lot of practice on this. But in general, if something has a net dipole, it's polar, and the dipoles don't cancel. If a molecule has no net dipole, then it is nonpolar. So these are nonpolar. Until you change one of the atoms, and then the forces are not equal and they do not cancel out, so now they are polar. Okay. Just to reiterate this point, remember that ions don't have dipole moments, so they can't be polar or nonpolar. They are ionic. That is definitely a distinction to remember. Okay, so for the last part of this video, I'm going to let you draw some of your net dipole moments, draw out your vectors, your dipole moment arrows, and try to figure out if the following molecules have dipole moments, have net dipoles or not. So the question is, which molecules have an overall net dipole moment and which do not? So if it has a net dipole, it's polar. If it does not, it is nonpolar. So you will need to look at each of these molecules. You can model them in Molecular Constructor if you like, so you can see the 3D shape. We have a couple here for you already. N2O is over here. NH3 is over here. This is the same shape as SH2. And yeah, okay. So you can run through these in Molecular Constructor and think about the net dipoles. I would suggest that you draw these as well so that you can see the arrows and whether they cancel dipole moments or not. Okay, so let's go over how to answer these questions. So if you drew out your NH3, we're going to find that it is tetrahedral, but it's a trigonal pyramidal structure, meaning that the hydrogens are all, they're pulling differently. So we have our vectors here, our dipole vectors, showing us that all of the electronegativity is being pulled towards the nitrogen. There's no downforce to cancel these out. So this has a net dipole. Net dipole, like that, because there's no force canceling it out. Let's take a look at N2O. I'm going to go over here and draw on this molecule. If you look at your Pauling scale, oxygen's more electronegative than nitrogen, so it's going to pull this way. Boop, boop. There's no force to cancel this out. There's all this down force and no up force, so this is another example of a net dipole. Let's take a look at HCF3. If you modeled this, carbon, hydrogen, fluorine, fluorine, fluorine. So these forces are going to cancel each other. Remember, fluorine is the most electronegative element on the periodic table, so your arrows will definitely point towards fluorine. Okay, so those cancel each other out because they're equal but opposite directions. But if we look, we've got a fluorine down here pulling. We've got a hydrogen up here pulling, but the hydrogen is going to pull a lot less than the fluorine. So if I was going to draw this correctly, I'd actually draw this arrow much larger. Sorry, I'm slacking. Okay, there we go. So they're much bigger than the hydrogen arrow because that's a much bigger dipole moment there. So this would also have a net dipole. Carbon dioxide. Oh, carbon dioxide's up here. Great. Okay, so we don't have to model this one. Oxygen is more electronegative than carbon based on where it is on the periodic table. So it's pulling the electrons towards itself, and we see that these are equal but opposite forces. They cancel each other out. So this one is no net dipole. Okay, so this would be nonpolar. Whereas all the other ones so far we've looked at are polar. Let's take a look at AlCl3. AlCl3, we're going to have Al. So you would model these in molecular constructor. That's how you would know what these shapes are, is it will do it for you. On exams and stuff, for this topic, you will be provided these shapes. For future topics, you will be expected to make these shapes because you're going to learn how to do them. But for this one, you'll be provided the shapes. If you look at the periodic table, you'll find that chlorine pulls more than aluminum, so it's going to pull the electrons towards itself. This is one of those shapes I told you to watch out for. It's got that trigonal planar structure. It's flat. We have these components of our chlorine arrows that go like this and like this. And so because of this, all of our dipoles actually cancel out for this one. So there is no net dipole moment because the over components of our dipole arrows cancel each other out, and the down components also cancel each other out. So this one is nonpolar. Let's take a look at SH2. SH2 is very similar to water. So it's got the sulfur here with two lone pairs, and a water and a water. And just like water, the sulfur pulls electrons to it. It's more electronegative than our hydrogen. Doop. You see that the arrows are pointing up. There's nothing pointing down to cancel them out. So this is definitely polar. It has a net dipole. Okay. So this one is polar, 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 and polar. And then the other two are nonpolar based on your structures.